Do you want a simple way to confirm an unpowered installation meets fault loop impedance requirements? AS-NZS 3000 has an easy solution. Let's get started. When verifying a new electrical installation, circuit resistance readings are taken and compared against values in Table 8.2 of AS-NZS 3000. This is used to confirm that all circuits meet fault loop impedance requirements. The stated resistance values in this table are calculated to allow for cable reactance and operational temperatures. The resistance test carried out during verification can only confirm that the internal component of the fault loop complies with the requirements of Appendix B of AS-NZS 3000. Now, let's look at figure B5 in Appendix B and consider the entire fault loop path. The installation itself is called the internal component of the fault loop. The other component of the fault loop is the network supply system, which is referred to as the external component of the fault loop. The loop path in diagram B5 can be followed using the indicating letters A to H. The directional arrows in the figure clarify the path taken by fault current. Starting at point A, which represents a secondary phase winding of a distribution transformer, we follow the service lines to point B and the point of supply. From point B to C via consumer's mains, we are now in the electrical installation. Points C to D represent a protective active circuit conductor connected to a piece of equipment. At point D, the fault appears as a short circuit to the equipment enclosure. Point E represents the protective earth wire from the equipment returning to the earth bar in the switchboard. The path continues from here through the MEN connection in the switchboard to the neutral bar, represented by the letter F. The consumer's mains neutral returns circuit current to the point of supply at G. Then through the service lines back to the supply transformer star point at point H. This completes the fault loop path. Clause 5.7 of AS-NZS 3000 outlines effective fault protection through automatic disconnection of the supply. When a fault occurs, the protection device needs to operate and clear the fault in the shortest possible time. Circuit protection devices must meet specific fault clearance requirements set out in Australian standards to limit energy let through under fault conditions. For this to happen in the real-world situation, the installation and external fault loop impedance values must be collectively low enough for sufficient tripping current to flow through the protection device. Higher current levels through the protection device will ensure the fastest operation, with minimal heat energy build-up in circuit conductors. Cables and protective devices are coordinated for optimal, practical and safe operation under fault conditions. Temperature rise in cables must be limited to prevent heat-initiated fire. The network-operated distribution cables are larger than individual installation cables and therefore have much lower impedance. However, as the external part of the fault loop, they will still contribute to the overall fault loop impedance values. This is why a fault loop impedance verification test is recommended to be conducted using a suitable meter once power is available. Next, watch this video to learn more about fault loop impedance calculations and maximum circuit lengths.